Atomic structure in symbolism represents how atoms are comprised of their parts and the symbols on uh, how we express these symbols with letters. So the nucleus has much of an atom's atomic mass. Protons and neutrons, they're much heavier than the electrons, and electrons tend to occupy almost all of an atom's volume. So this is telling us the actual diameter of an atom and the diameter of the nucleus. It's a bit difficult to think about these numbers in terms of scientific notation because uh, they are so small. So I think it's a little bit easier to take a look at a diagram of this. So here's the nucleus. It's 10 to the negative 15th is 10 to the negative 15th meters is its diameter. The diameter of the entire atom is 10 to the negative 10 meters. That's that is if we're thinking in terms of real life in a scale of the real world, we can think of a large stadium of people, the entire stadium being um, the entire atom with here's the electron cloud and the nucleus in the center. And the nucleus would be the size of one blueberry. And I put a very small red dot there. And in fact, that blueberry would be even smaller than that red dot. So that's just to help you to understand the size of the nucleus compared to the electron cloud. Next, we're going to talk about units. So units have to do with we have to express everything in the correct amount of units. So when we're talking about weight, we're going to express units in grams. And if something is very small, it's going to be 10 to the power of a negative number. So that's how we express scientific notation of very small values. Electrons that have a charge, excuse me, electrons, they have a charge of less than 2 times 10 to the negative 19th coulombs. And previously we found the exact charge. We call the fundamental unit of charge, lowercase e, 1.602 times 10 to the 19 coulombs. We also refer to some other units that we refer to is atomic mass, and we abbreviate that AMU. You can find the atomic mass on the periodic table. It will tell you specifically the AMU of these different elements. And we base AMU from carbon 12. So carbon is on the periodic table. If you find carbon on the periodic table, it has exactly a 12 AMU. Protons have roughly a mass of 1 AMU. It's slightly more. We say they have a charge of +1. Neutrons have almost the identical mass of a proton. It's just slightly heavier, but for simplicity's sake, a lot of times we just round the mass to 1. Neutrons have no charge, and electrons we can write in terms of AMU is 0.00055 AMU. And we say it has a charge of -1. The atomic number is how many protons that are in a nucleus. We represent the atomic number as Z. And its value determines the identity of an atom. So what this means is we can figure out what these different atoms are depending on how many protons that they have. So here's the periodic table here. Hydrogen has 1 proton, and that's what makes it hydrogen. Uh, as we continue down the line, we can check to see how many protons that each of these elements have. Here's boron, that has 5. Uh, carbon has carbon has 6 protons, and its atomic mass is protons plus neutrons. So carbon carbon is carbon 12 in its most natural state. The atomic mass, the exact atomic mass, according to this periodic table here, says it's 12.011 U, and sometimes we write U instead of AMU. So that's the equivalence for AMU is U. So protons determines the element, and then protons plus neutrons is atomic mass. A neutral atom has to have the same number of positive and negative charges. Not all atoms are neutral, but we do tend to work with neutral atoms more frequently than not, where the number of protons is equal to the number of electrons. The mass number, I believe I mentioned that while we were looking at the periodic table, but let's go over it one more time here. So the total number of protons and neutrons is the mass number, and we call that A. The number of neutrons is the difference between mass number and atomic number. So atomic number Z is number of protons, and we can find the mass number by adding protons plus neutrons. If we want to find the number of neutrons, we can subtract the atomic number from the mass number. So atomic number tells us number of protons, mass numbers, protons plus neutrons. If we subtract the difference, we are just left with neutrons. When protons and electrons are not equal, we say that the atom is electrically charged, and that's called an ion. Ions can be positively or negatively charged. To find the charge of an atom, we start with the number of protons and subtract the number of electrons and find the difference between the two. If there are more protons than electrons, then we have a positive ion. If there are more electrons than protons, then we have a negative ion. And atoms and even molecules, they acquire charges by losing or gaining electrons. So when we have a negatively charged ion, we call that an anion. So an example is we have a neutral oxygen atom where Z equals 8. Remember, Z is the atomic number of protons. So oxygen has 8 protons, and if it's neutral, it also has 8 electrons. If it gains 2 electrons, it will have a -2 charge. And we don't write -2, we write 2 negative. We write it as a subscript. It sort of looks like an exponent on a number. So for this, or the oxygen that is a -2 charge, I've written the exponent part there already, but it would look like that as a cation with a -2 charge. If an atom loses 1 or more electrons, it's going to have a positive charge. So there's going to be more protons than electrons. A neutral sodium atom has 11 protons and 11 electrons. This is Na on the periodic table. And if this atom loses an electron, it will become a cation with a +1 charge. And again, we're just subtracting the number of protons and electrons to find its overall charge. So here is sodium with a +1 charge. We just write a plus. Usually we don't write the 1 there, but you could write it like that if you want to. Normally we just write sodium ion as Na+. Chemical symbols, I've already written a few of them, and we've looked at them on the periodic table as well. These are all abbreviations that we use to indicate an element or an atom of an element. Some of these symbols, they don't quite correspond with how the names seem like they would be. But that has to do with where they originated from in the language that they originated in. So the symbol Mercury is one of those that's what you just have to remember. It's Hg. Some symbols are derived from the common name of an element, and others are abbreviations from other languages. Most of these symbols have two letters. We've used three letters before for atomic numbers greater than 112. And only the first letter is capitalized. So that's how we can tell the difference between these different elements when we have a lot of them written out. That that's uh, that's very important that we capitalize only the first letter. Here's mercury. It's in a liquid state at room temperature. These are some other common elements and their symbols. So aluminum, bromine, calcium, uh, carbon, chlorine, chromium, cobalt, copper, fluorine, gold is one of those interesting ones. It's Au, helium, hydrogen, and iodine. That's from the first list here. And then here are some others as well. Lead is another, lead and iron. These are all worth memorizing and definitely become more and more familiar with the periodic table as much as you can. There's a lot of different trends, and it's good to just have a periodic table whenever you're doing anything related to chemistry, just to have one nearby. Isotopes. We're going to talk about isotopes when we get to nuclear chemistry. Um, but for now, this is just a basic overview of what isotopes are. Uh, the atomic number, sometimes we write it as a subscript to the left of a symbol. So, for example, magnesium, it exists as three different isotopes: magnesium 24, magnesium 25, and magnesium 26. All of these isotopes have 12 protons still, so it's still magnesium. If we go to the periodic table, take a look here. If we go to the periodic table, it has 12 protons, still magnesium. But when we check the atomic mass of magnesium on the periodic table, it says 24.305 is the AMU. But here we have these different isotopes of 24, 25, and 26. So the reason that it's 24.3 on the periodic table is what we've done is we calculate the relative abundance in terms of percentage of these different values, and then we find the overall weighted mean of what that equals. And it's essentially the average, but we calculate it a little bit different than just the average. We would use the weighted mean calculation. But these isotopes, they all have different numbers of neutrons in them. So they all have the same protons, but these other isotopes, they have more neutrons than magnesium 24. So here's how you would see all of these numbers written on the different elements. So here's helium. If we find helium on the periodic table, let's start with doing that first. So helium is number 2 on the periodic table. That means that it has 2 protons. Its atomic mass is 4. That's its AMU. So that means it has 2 protons and 2 neutrons, giving it an AMU of 4. So now if we go back here, the AMU is 4. The atomic number, a lot of times we don't write the atomic number. I think that's a little bit strange that we don't, because when we look at the periodic table, that's the main number that it tells us, the number of protons. But in fact, a lot of times we're just given the mass number. And the mass number, again, is protons plus neutrons. So we write that on the upper left, we write protons on the lower left, and then we write the overall charge on the upper right. There are some types of hydrogen, some isotopes of hydrogen. One of them is called protium, and that has a 99.9% natural abundance. So when we speak about hydrogen, we are we are almost always referring to this type of hydrogen. But there are other types of hydrogen as well. Deuterium and tritium are are these different isotopes of hydrogen where there's more than there's still one proton, but there's more than one neutron. So deuterium has two neutrons, tritium has three neutrons. So they all still have the one proton there. The neutrons number has changed, and that changes the mass number as well. So again, each proton and each neutron has a mass of roughly 1 AMU, if we are to approximate that. Um, and the electrons, they weigh far less than protons and neutrons. I believe I talked about this already, about how elements have a mixture of two or more isotopes, but let's go over an actual numerical example now. So to find the average mass of something, we take the sum of, that's what this symbol means the sum of, and then the fractional abundance or the percent abundance times its actual mass. So letter B is on our periodic table. This is for boron, and it has two different isotopes. One isotope is boron 10, and the other one is boron 11. So if we check to see this on the periodic table, let's take a look at what boron tells us when we just click on the periodic table. Here it says boron has 5 protons and an AMU of 10.81. So let's see how they're able to calculate that. So boron 10 has an abundance of 19.9%, and its AMU is about 10. Boron 11, it has an 80.1% abundance, and it has a mass of about 11 AMU. And so we want to find its average mass. And to do that, we're just going to multiply the percent times the AMU plus percent times the AMU. And then we just add those together and we get 10.81 AMU. Now, finding what the percent abundance is, that becomes a little more complex. But if we do know those abundances and we know the AMU of both, now 10 and 11, this is very close to 10, but it could be, if we use the number 10 and the number 11 instead of going out 4 decimal places, we might get a slightly lower number than this. So knowing these exact values can be challenging, but I think what's more important is just knowing how we can find this average mass. Mass spectrometry has to do with using an instrument called a mass spectrometer. A sample gets vaporized in this electron beam, and it causes the atoms to become electrically charged. And then this happens because they're losing one or more electrons. Then the cations are separated by their mass and their charge. And this is just a mass spectrometer diagram. And it shows the mass to charge ratio depending on the relative abundance of each of the percentage of the atom. All right, and here are the practice questions. for this section.